Well, good morning, ladies and gentlemen. I'd like to start the plenary talk today. I'm Hajime Asama, the President-elect of Ifac, and I'm the chairman of this plenary talk. Today, we have very special, wonderful plenary speakers, and I'd like to introduce two of them from Airbus. First speaker is Mr. Charles Champion. I'd like to briefly introduce his biography. And he was appointed president of Airbus Operation SAS in 2015, in addition to his position as executive vice president engineering in 2010. In his role as executive vice president engineering, he is responsible for research and technology over our product architecture and concept development and design office, integration and flight testing, and continued product airworthiness. He is a member of the Airbus Executive Committee. Additionally, he was appointed the chairman of the fully owned subsidiary Airbus India, created in 2014. And he has a lot of careers in Airbus. And from 2007 to 2010, he was executive vice president in charge of customer services, responsible for support of all Airbus aircraft around the world for the development of services for Airbus customers. And he graduated from the École Nationale Supérieure d'Aéronautique et d'Espace. I'm sorry, I'm not good at French. In Toulouse in 1978, and holds a Master of Science degree from Stanford University. Today, he's going to talk about avionic or airplane side story for Airbus business. And another plenary speaker is Ms. Grazia Vittadini. And I'd like to also introduce her biography briefly. And she was appointed executive vice president, head of engineering in January this year. And she is member of the executive committee of Airbus Defense and Space. So previously, she served as senior vice president, head of corporate audit and forensic, responsible for Airbus Group audit activities worldwide. She was also vice president, head of airframe design, technical authority for all Airbus aircraft. Currently, she serves as diversity steering committee. She graduated from the University of Politecnico di Milano in aeronautical engineering in 1998. She's going to talk about the defense and the space side of the Airbus business. So let's welcome two of them.
Thank you very much, Mr. Chairman, for your nice words. I must say one of the struggles we have in our industry is parity, but I'm really proud to be able to do that presentation together with Grazia today, just to show the scope and the range of course, what we do in Airbus, but also what are our challenges when it comes to automation. Right, I hope you will follow me. It's early in the first day. Just a few words about Airbus, because I know there are people from many industries and institutes in this room. Airbus is it's basically a commercial aircraft manufacturer, but also with two main divisions, helicopters and defense and space, with a wide scope of challenges. Grazia will talk to you about that later. It's a workforce about 144,000 people, 67 billion revenue, and what is a characteristic of our industry, an order book of 1 billion euros, or a bit more than $1.2 billion, a very large order book, particularly in commercial aviation. Coming to commercial aviation, So we have a turnaround of around now 50 billion euros, 52, 55 billion dollars. And what's important is we have an order book which represents almost 10 years of production, depending on the model. Why is that? Because basically, it's a huge industry. We have 3.6 billion passengers and 50 million flights. It represents, in terms of GDP, the equivalent of Poland. But it's a challenging industry, and I would just like to share with you what are the challenges in order to certify an aircraft, in this case the 350-1000, which is currently in flight test in Toulouse. So I think this is a challenge which illustrates what our industry is about. You have to do and design an aircraft that, first of all, is safe. Safety is in our DNA. We are carrying passengers. And also tested at all extreme conditions. And even at extreme conditions, and depending on the failure modes, the aircraft has still to be safe. And this is what is driving one of the complexities in terms of automation related to aircraft. It's not just doing simply an automation curve, it's basically thinking what can happen if, and what can happen if in all circumstances. In the case of the 350-1000, we just completed our high temperature test in Alhain, and we are planning to certify the aircraft the last quarter of this year. If you look in the sky, maybe you will see one of our aircraft flying today and tomorrow, because we are really in active testing. So that is about what our business is about. It's more to illustrate the product and what is behind. What are our challenges, and what is our automatic and control journey? In terms of challenges, very simple. We are in a growth industry. So you can look at all the various provisions done by the different stakeholders. We always are between 4 and 5% per year. This represents doubling the number of revenue passenger kilometers, which is the way we count our volume of traffic. every 15 years. Every 15 years, you double. Of course, there are ups and downs depending on the crisis, but on the long run, this is true. Will it be true in the 30 years to come? Well, if you look at emerging areas where basically like Asia, China, there is a strong demand, and the more people earn money, the more they want to fly. Obviously, this growth is here to stay, at least for the coming years. But this is a challenge, both in terms of handling the volume of traffic, but also in terms of associated safety. The other challenge is sustainable growth. Even though aviation is probably 2% in terms of CO2 emissions, clearly we are visible, and we have to understand how with this growth we can manage to actually keep our levels of environmental impacts as low as possible. As an example, with the European Union, the challenge 2050 has been defined. Compared to year 2000 standard, which is the current A320 flying in most of the airlines, it's a reduction of 75% of the CO2, 90% of the NOx, and 65% of the noise. This is huge for us. We did it in the past, but we have to find the ways in order to be able to deliver that in the future. It's about research and technology, but it's also about automation and thinking systems of systems, how you manage in the most efficient manner the aircraft in the overall air traffic system. For us, the challenges are clearly around that growth, traffic doubling every 15 years. The flight path 2050, what we want to do is to have a carbon neutral growth industry. And of course, I will just mention competition, and it's true that in our business there is a strong competition from all the in-place players, but also from new emerging players in this world, and nothing is better than competition in order to be able to force you and your teams to innovate and also go faster in the way you develop your ideas. But it is in our DNA, being a game changer. And if I come to automation, I will start maybe with the journey. When we started flying, it was in 1972. We flew the first aircraft, analog, a little bit of automation, of course, but analog. Automation because we had autoland already, Cat 3 landing in our jargon. It means that you land the aircraft almost with no visibility at all. But this was the limit of what you could do with analog type of approaches, and very also challenging in terms of flight controls, because the tuning of the flight controls comes from rods, springs, compensations, and very delicate type of rigging. And we actually were the first to introduce fly-by-wire on commercial aircraft. I know Dominique Chatronnet has made a large speech on that a few days ago. But the big idea was to go from analog to digital. We kept the rudder, actually, because we are very conservative. This is one of our other challenges in commercial aircraft. When you have to introduce change or innovation, you have to do a lot of tests, but you have also to convince the airworthiness authorities that this change is good and that this change is safe. And then you have to demonstrate by experience that the change is really worthwhile and safe, which means in our business, typically, sometimes it takes years in order to introduce an innovation. If I take the example of the rudder, we still have mechanical rudders flying on the 320s delivered today, and we have had the agreement now to switch to an electrical rudder, full fly-by-wire, in the next months to come. But this is really based also on the experience over more than 30 years of flying the aircraft. Because of course the rudder, mechanical rudder, was the last resort should you lose all your electrical power. So it shows the level of conservatism which has to be taken into account in terms of designing and introducing automation. Then afterwards, another big challenge we have are the cycles. You know, in the avionics industry, you have here cycles, software 6 to 12 months, hardware, it depends on the processor, it can be even less than 3 years. But aircraft, you know, you build the 320s, which were delivered in 1988, they still fly today, most of them. And you don't change something on the aircraft so easily because you have to go through the whole certification and validation process. If I take, for instance, A330, you've got the flight management and guidance computer, so a big beast which allows to manage the flight of the aircraft. We are using an Intel 286 16 megahertz processor. Maybe for the young people, this is already archaeological. Well, for me, I saw it coming. But basically, it shows that we have already to manage all type of processors that do the job in the frame of up-to-date computers, which are in the external world, and you have more power in your smartphone today than you can have in some of the computers we introduced, let it be in the year 95 or 2000. That's part of the challenge, and of course, new programs, they last from 20 to 50 years, and they take 5 to 6 years to develop. So this is what we have to manage, and this is particularly a challenge in terms of managing these different cycles, including the obsolescence. And when it comes to automation, this is a chart just to show the evolution over time and the complexity also behind. So, and the horizontal, you have the years. Vertical, you have on the top the lines of code, and at the bottom, the number of equipment. And it's kind of crude way to measure. So the 300, 1972, a few boxes, but nothing digital. The 310, we started to introduce some very little automation, electrical orders on the spoilers. 320, as I mentioned, the big change. We had almost 1 million lines of code. But then, of course, with all the complexity, the 330, which was the one afterwards, we started to think, how can we do differently? So we introduced computer head specifications, in particular with the SCADE, Safety Critical Application Development Environment, with generate specification. As a result, we managed to reduce the lines of code quite significantly, but the number of boxes was increasing because of the complexity. Then came the 380, so of course, even more integration of different functions. We're asking more and more, for instance, to flight control, so the lines are going up again, but the number of boxes are going, but not exponentially, because we introduced modular avionics, which is like having a PC on one side, and you've got functions like fuel, like air conditioning on the other side. And instead of having one box and a lot of software, including operating system for each box, you actually have the function on one side, which you integrate on the operating system of a modular avionic on the other side. So it simplifies, but it also increases complexity in terms of interfaces between the guys doing the function, the guys doing the hardware, and the guys doing the operating system, to simplify. And then with the 350, even more complexity, so we're going up again in the lines of code, but with the simplification of the hardware, rethinking a bit how we could actually introduce our redundancies and also extending significantly modular avionics, we managed to contain the number of boxes. What will be the next aircraft? I don't know, but I can bet with you that it will be even more complex in terms of lines of codes. And this is one of the reasons why this is our journey. Our journey, I took examples. We have limited time, of course, but I took one first block, which is about short-term improvements, which we're introducing. Our short-term, it means from months to years. And then afterwards, what are the different challenges in terms of automation we have to face looking forward beyond the horizon of our current type of products. I will start from brake to vacate. This we introduced on the 320. You arrive on a runway, you land. But if you brake too much, then afterwards you are using a lot of energy. And if you don't brake fast enough, then you miss the taxiway and the aircraft stays a long time on the runway. And one of the key issues with the airports, of course, is the sooner you free the runway, the more aircraft you are able to handle in a given time. So brake to vacate, basically, is an automation system which actually, a function of the position of the taxiway, manages the braking of the aircraft so you can exit optimizing the braking energy towards that taxiway. It implies, of course, the braking system, visualization, database coming from the airports, positioning of the aircraft on the airport, and so on and so forth. This we introduced on the 380, and we have introduced it on the following models. One example, but comes to the next one. That's a good idea, but what about the runway? If you look at safety, around 22% of accidents are coming from the aircraft veering off the runway from one reason or another. Why? Because, you know, unstabilized approach or wind changing quickly, you're a bit long, your flare is not good enough, and unfortunately, end of the runway, out you are. This, of course, is a critical element, so we have actually developed ROPS, Runway Overrun Protection System. The idea is in flight, this tells to the pilot, be careful, you do not have enough length in terms of runway. And once you actually hit the ground, it tells you basically if you have enough runway and also if you should brake harder in order to stay within the runway. Next enhancement is introducing also a real-time measurement of the actual state of the runway, snow, contaminated, slush, ice, water, so that actually you can optimize the system in order to be able to be sure that you get the right information and you are not too conservative. This is a typical example which we believe is going to make a huge difference on our fleets in service, and we have introduced it standard on the 350 and option on other aircraft. What is the business model? Because of course we are also in business, so where do we make money out of that? That's an interesting one because in fact the insurance companies agreed to reduce the premium for the airlines operating the system so that overall you balance the economics of the whole system. And this is also another element with automation. You need to think value for the customer and value for the business. Another example of complexity which is increasing the number of lines of calls. Flexible structure control law. 350-1000, we make a characterization of how the fuselage responds in terms of frequency. So in fact, basically, you have frequencies on the horizontal line. We're talking 1 Hertz, 5 Hertz. And then you have the peaks of acceleration on the other side. So of course, if you start to have acceleration in cruise, this is not really comfortable for you as a passenger. What can you do about that? And of course, there the idea using sensors and accelerators is to play with the flight controls, the rudders, the ailerons and the elevators in order to reduce the peak of gain and have a comfortable flight. So in this chart, the high peak on the pink curve, I believe, shows that you have no gain and no automatic control. And with the blue one, you actually equalize the peaks and you make a more comfortable ride. The price for that, of course, is that you're using the ailerons and the elevators for what they have not been designed for, which is controlling the aircraft, but in order also to help the stabilization and the comfort. More complexity, but with an excellent result at the end. And a last example I will show you is advanced fall detection. Alors, on the top, you have the classical curve about an actuator. So you have the input. I will not dare to make you an explanation on that. And then you measure the output and you loop around. Question is that we are in aircraft industry. So what happens if the actuator has an electronic fault and start to move either in the wrong direction or to the limit of its direction? Then afterwards you have more force, you have to counter the force. This has a repercussion in terms of how you design the structure of the aircraft. The clever part there is that on the top you have the classical loop, and on the bottom you have the same loop based on the model. So you compare in real time, a few milliseconds depending on the conditions. I won't go too much in the details. You compare the actual output against the model, and if you see a deviation bigger than a certain value, then you detect that there is a fault, and then you actually deactivate the actuator and you go to the backup mode, which allows you not to take this case in consideration when you design the aircraft. What is the net benefit? 40 kilos. What is 40 kilos? Half a passenger. So this is how you can intelligently use a classical extended Kalman filter in order to go one step beyond in terms of intelligence on board the aircraft. Afterwards, for the future, we are looking at formation flight. We actually flew 400M behind another 400M, and we saw there could be up to 10% benefit. You know, it's like birds. When you see a flock of birds migrating, you will see that the one in front sometimes goes behind, another one goes in front, so that in fact they share their energy in order to go further as a group compared to individually. The idea is exactly the same here for aircraft in order to fly in the vortex, and to do this and to demonstrate really the viability, we actually did a more recent flight test. This one is from October last year, demonstrating how we could do formation flying. So, of course, the white vortex on the 380 were for visualization only. It's not like that on the normal aircraft. It shows a potential up to, as I said, between 5 and 10%. What are the challenges? Well, the first one is in terms of automation, of course, because you don't want to burden the pilot on top of his flying the aircraft and navigating the aircraft. So this is about sensors, and this is about a control loop, which allows you to keep the aircraft in the vortex of the preceding aircraft. The other challenge is, of course, business-wise. How can we make this work? Because the one in front has no benefit, but the ones behind have got the benefit. How do you share the benefit? And this is typical of the type of challenges in our industry. It's not only about developing a good idea and implementing it. It's about working together between the manufacturers, the airlines, the air traffic management, in order to have a better way and to be more efficient. And this is typically what we have to do. This is why also we decided to invest in CESAR, which is the European joint undertaking for the traffic management of the future. And we are also in NextGen in the US. And we work closely with Boeing on that one, because what is important, of course, is to define standards which are valid across the industry. And this leads me to my next example, that 4D trajectory exchange. So what is 4D? It's basically simple. It's 3D plus time. If you look at an efficient aircraft today, we are fighting to gain 5, 6%, 10%. Well, we managed 15% in case of the 320neo against the previous version. But these percents, you can lose them very quickly when you circle around Heathrow for 15 minutes or 20 minutes before landing. And the same applies in all the major hubs, which means that a lot of the challenges related to Flight Path 2050, maybe half of them, are related on the management of the aircraft in the overall system of ATM, so that the aircraft can land precisely when needed and is neither too early nor too late. So for this, we developed the 4D application. We actually demonstrated live already. It implies, of course, much more dialogue between the aircraft and the air traffic management. So typically, you have a data link, by which the aircraft sends the position and also the flight path. Then, basically, as long as it moves on, air traffic control comes in the picture and actually understands what is the window of opportunity for an aircraft to pass through a given point. And then based on the traffic and the optimization in order to be able to actually clock the aircraft one behind the other and land in the most efficient manner, you actually negotiate between the aircraft and ATM a window of passage at the waypoint, plus or minus 10 seconds, in order afterwards, based on that, to manage the flow of aircraft. Big advantage is, of course, if you are early, but you cannot be too early at arrival, instead of burning fuel and then having to wait, you actually burn less fuel and arrive on time. And at the end of the day, in terms of air traffic management, this, of course, requires a lot of intelligence to manage the flow of aircraft flying across the airspace. This is basically what we have tested already, at least 2 times, and it is what is behind CESAR, as an example, in terms of optimization of air traffic management. And the aircraft goes in the window, and the job is done. Afterwards, we are not only looking at aircraft, we are looking at urban air mobility. So this is more at the overall Airbus level, because it requires competences from helicopters, defense and space, us. So we all work together. And the idea is, how can we further develop urban air mobility, particularly in large cities where there is a big issue. Alors, we have several projects on that one. We have seen many in the press already. I will just mention Voom. Alors, Voom, the idea is to have an app like for a taxi or a car, where you can actually ask for basically a flight to go from point A to point B, and then afterwards a helicopter will come and fetch you. We tested that at Rio during the Olympics. It was good because it allowed to demonstrate there is a market, also have an understanding basically of what would be the acceptable cost for such a service, and now we can actually manage the fleet. So this is, I would say, also showing that it's not only about the technical idea, but also how you develop the business in parallel. Afterwards, Vahana is our A-Cube incubator in San Jose, close to San Francisco, where they are developing an autonomous vehicle flying alone with one passenger on board. Then we have City Airbus, which is more, I would say, the helicopter of tomorrow. The idea is to have a pilot and be able to fly up to 4 passengers. And then Skyways, which is more for managing traffic, because there again, there is ATM at the level of the city. And the idea is working with Singapore to see how we could do and manage parcel delivery in a very dense environment. And finally, Pop-Up, which is more a concept about the future. So on that one, I will just show you a video on Vahana, just to give you a feeling of what we are working on, knowing that the first flight experimental is scheduled for end of this year. Cool, huh? Hopefully we'll see that flying in urban cities in the years to come. So just as a wrap-up before I hand over to Grazia, I think we have built an expertise in automatic and control, and we are continuously improving in that direction, not only with new aircraft, but also improving our existing products. And this is part of the solution to the challenges I mentioned before, particularly the environmental and the growth challenge. Also, integration now is not only within each system, but within systems on board the aircraft, within aircraft themselves, and also with air traffic management and airports. This is very important, not to mention, of course, the passengers. And I think there's only one point I would like to make before handing over, is that we need you, because this is a community work. We need a research institute, we need also universities, partners, in order to move forward and define together the future of air mobility. Thank you.
Thank you very much, Charles. So please bear with me due to encryption, defense encryption on my memory key. I'm going to have to connect the laptop. If it will not work, I will blame in best industrial standards IT, but it looks good on my screen and also on yours. Perfect. Thank you very much for having me today. It's a great honor and a privilege to have the opportunity to introduce to you, elaborate a little bit on the achievements and the challenges of automation and control related to defense and space, and more specifically to the realm of space systems. And it's also a very specific, particular moment for me. I come from 15 years of engineering within Airbus Commercial, and therefore, having the opportunity to speak right after Charles, who has been my inspirational guide and mentor for so many years, is a very, very special moment. So without further ado, I will start by showing you a short movie giving a flavor of the amazing richness and diversity of portfolio when it comes to Airbus Defence and Space. So indeed, Airbus Defence and Space comprises military aircraft, space systems, communication, information and security. But today, the deep dive will be in the space system realm, starting by the significant achievements across our product portfolio when it comes to automation and control. Starting by the specific realm of space science and exploration, where most technologies currently in use in our commercial spacecraft, be it telecommunications or Earth observation, were tested and developed first for science and exploration, based also on more than 30 years collaboration with ESA. For instance, Rosetta, the Comet Explorer, launched in 2004, has seen for the first time the use of our scientific camera, OSIRIS, with our first silicon carbide optical instrument. Gaia, the astrometry mission launched in 2013, saw for the first time a telescope built with a very large silicon carbide mirror. Looking ahead at tomorrow's mission, you see Bepi Colombo, the first European mission to Mercury, with launch planned in 2017. 7 years cruise envisaged with a high-performance electric propulsion. We have the ExoMars rovers, landers for Mars, planned to be launched next year with very specific thermal protection challenges and the solutions. I will elaborate in a bit more detail on JUICE. JUICE is the mission envisaged to explore the icy moons of the planet, of Jupiter. And last but by all means not least, Orion. Our participation to this program in an international partnership with Lockheed Martin really demonstrates that Europe still has a significant role to play when it comes to human space flight and scientific research in low Earth orbit. So, space science and exploration, achievements thanks to automation and control, telecommunication spacecraft. Here, the challenges are slightly different. We are moving more and more towards an all-electrical satellite concept, which enable accommodating the same mass under the same launcher, Ariane 5, as illustrated in this case. We are looking to the development of Ariane 6 and contributing to it. But what really does change is the payload capacity. Thanks to an all-electrical concept, we can go from 16 to 26 kilowatt. It's nothing new, meaning we've been flying with electrical propulsion on the Eurostar 3000 series already since 2004. Yet, back then, the engines, the power available limited operations to station keeping. Whereas now, we have a new generation of plasma thrusters, which allows us to propose not only station keeping, but also orbit transfer, orbit raising from the transfer to the geostationary final orbit in around about 4 months, which is a long period, but is something the customers are looking into with a lot of interest, and they are ready to accept due to the significant mass savings that electric propulsion allows. And mass is cost related to specifically the launcher phase. So the new generation of satellites, the Eurostar NEO, is being developed with, by default, this EOR, the electrical orbit raising feature, as one of its main key parameters. Looking a bit more to the future, we have Quantum, our European program, where we really do believe that telecom satellites with a fixed mission lasting their whole life will soon appear out of age. And so with the flexible payload concept we are developing for quantum, we will be able to fully reconfigure and reprogram the mission in orbit, providing so total mission flexibility in frequency, coverage, power, and bandwidth. So reconfigurable through software update by telecommand. When it comes to Earth observation, we have Helios, CSO, Pléiades, very agile maneuvering and high precision pointing platforms, where we do introduce for the first time the use of fiber optical gyroscopes and control momentum gyros. And more, let's say, in the German part of our division, in the German teams, we have developed TerraSAR X and Tandem X, X-band synthetic aperture radars, and last but not least, Perusat, basically an Earth observation spacecraft using the latest evolution of the Astrobus family concept. It's the smallest size of this specific modular development with very highly stable optical structure, also in silicon carbide, and new generation detectors. Overall, a very high performance platform. We are also very active in when it comes to climate and environmental monitoring. So space has become an undisputed diagnostic tool to detect climatic and environmental changes on a planetary scale. We have developed a very broad array and range of products for climate monitoring, more generically for Earth observation. Basically studying the Earth in every possible band, using every possible sensors. So we will have, for instance, multispectral sounders. We have a broad range of synthetic aperture radars. We have lidars for various applications, such as understanding the impact of clouds, measuring the wind speed, detecting methane in the atmosphere, plus a whole set of bespoke instrumentation for the Sentinel and EUMETSAT meteorological missions. Stakes in this segment are particularly high, since good planets are difficult, are hard to find, and we better do all we can to monitor our very own. When it comes then to OneWeb, here we are looking into a paradigm change impacting the space industry. Why? Because we are in a partnership with OneWeb satellites to develop, to design and manufacture 900 satellites. We will be going from the order of magnitude 10 satellites manufactured in 1 year to 3 to 5 developed, manufactured in one single day. So with the intent to have a constellation offering high speed, low latency, interconnectivity, internet connectivity globally, worldwide. So we're talking about satellites, just to give you an idea of the dimension of a washing machine, 150 kilograms, more or less, planned to function in orbit for up to 10 years' time in low Earth orbit. We will start delivering in 2018. And again, it's really a revolution in satellite manufacturing. The first 10 will be manufactured here in Toulouse, and our colleagues from Airbus Commercial have been key into helping set up what we call now really a final assembly line for these satellites, following the same principles and criteria Airbus Commercial uses on its wonderful commercial airplanes. Orbital systems, we have a very strong heritage, and this is the ATV, the Automated Transfer Vehicle, which operated between 2008 and 2015, servicing the ISS, the International Space Station, with 5 consecutive successful missions, carrying in space up to 7 tons of payload, cargo reboost capability. This is the largest payload capability of the ISS ever transported. And all what we have learned out of this experience on the ATV, complemented with the latest developments in terms of in-orbit rendezvous capabilities and electric propulsions, are the key for the future endeavors in our portfolio, such as Orion, already mentioned earlier, and Space Tug. Space Tug is the main element of a totally new business segment under development in space. It's based on on-orbit servicing of satellites to repair them, to maintain them, to refuel them, to provide also de-orbit support to enable re-entry into the Earth atmosphere of spacecraft after they have completed their mission. And if we succeed maturing the key technological features to enable such a Space Tug vehicle, we will definitely change our approach to go to space and the way we do things when it comes to space systems. This was so a brief overview on the achievements so far. Let's have a look more in detail at the automation and control challenges for the future. Specifically, when it comes to telecommunication missions. The aim, so it's a highly competitive market, so reducing the cost is absolutely fundamental. And that's why we introduce electrical orbit raising to allow the reduced price of payload. But we are also going for a total electric propulsion concept. What you see in the movie is practically the translation of the telemetry, the actual telemetry data we have analyzed on Eutelsat E172B, launched at the beginning of June. The thruster on this specific satellite is no longer fixed. It's installed on the robotic arm, which deployed, as you have seen, via the telemetry data, synchronously with the orbit. The attitude control is fully autonomous, so the actuators are commanded automatically based on onboard sensors outputs, whereas the trajectory of the spacecraft is semi-autonomous for the time being. So the orbit determination is performed regularly on ground based on RF ranging. Orientation of the thrust is then computed on the ground with optimization software modules and uploaded via TC, via telecommand, to the spacecraft on regular basis. So with this type of solution, we can offer reduced payload mass, reduced price for our customers, but we do significantly increase the complexity of orbit and attitude control systems. Let's look at the challenges when it comes to Earth observation. We are now required more and more to re-enter the Earth atmosphere, as I mentioned earlier on, to avoid creating space debris. This will mean having on board more fuel with bigger tanks and with increased challenges due to sloshing of fuel in the tanks. So there is an interesting picture there on the left side of the screen of a fluidics experiment done lately by Thomas Pesquet in microgravity environment on the International Space Station. Practically, the experiment consisted into applying acceleration to a reduced size tank, recording the forces and the torques applied to the liquid in motion in the tank, with the goal to develop simplified sloshing models to be then fed and incorporated into our spacecraft dynamical simulation, to be able to develop active control methods to mitigate the sloshing effect. When it comes to future exploration missions, well, on Earth we have a universal, very cheap position sensor, that is GPS, which can also be used in low Earth orbit environments, but definitely not when it comes to interplanetary missions, right? Or when it comes to landing on an asteroid, like we did with Philae and Rosetta. We need to go to places we've never been before to, and landing on unknown bodies, very likely non-spherical bodies, meaning our algorithms need to be reviewed in the sense, and we need a total new navigation and guidance scheme to enable this. And we are indeed developing an innovative vision-based navigation algorithm set using feature points tracking for landing on small and irregular non-spherical bodies. And you see the example of Philae landing pictured by Rosetta and modeled on the left bottom side of the screen. We're investigating the use of guidance algorithms derived from sampling-based motion planning techniques to design the autonomous replanning of proximity operation trajectories in environments as complex and constraints as this. And to give you a bit more of elements on Jupiter, which I mentioned earlier on. So a little movie. JUICE is planned for launch in 2022. Arrival to Jupiter 2030. And a mission of 3 years of detailed observations of the giant gaseous planet and 3 of its largest moons. So very, very specific and complex challenge. Going further away from the sun requires bigger and more complex vehicles, having more solar array surface to begin with, positioned in this specific case in a cross configuration, in a cross shape to avoid the traditional flexible beam effect. And we will also need to have on board more fuel. So we have a bigger structure, more flexible, with enhanced sloshing modes, disturbing very much the spacecraft, and as a consequence, the control engineers having to take care of the guidance, navigation, of control of such a system. Launch cost is what normally drives the cost of a mission, meaning we are aiming to save as much as possible weight on our structure, meaning an additional factor of flexibility. It is a very, very complex set of parameters due to the flexible mode combined with a highly disturbing torque coming from engine misalignment, big tanks, huge solar arrays, and firing in a full, as we call it, flyby configuration. So we will be shifting orbits with solar arrays fully deployed. So it is indeed a significant challenge where we will need smart control techniques to decrease the excitation of solar arrays in particular. This we will achieve by different, in a twofold manner. So shaping the acceleration profile of the engine to limit the flexible mode excitation, but also including active flexible mode damping with reaction thrusters in case the main emergency thrusters fail. So you see a video with the solar array excitation induced by the engine firing with and without the shaping. So it is quite a significant difference. And also a very simple illustration of the principle of the emergency damping loop. Back to space orbital systems. So if we want to apply the benefits of electrical thrusters also to this realm, we need to go for totally different guidance systems. And if we want to keep the costs contained, we need to go for an optical rendezvous sensor solution. And so we have worked in this sense on enhancement of classical position control practices, considering model predictive solution to consider explicitly the differences between the hybrid plasmic and chemical nonlinear actuation constraints. With chemical, you can fire practically whenever you need, whenever you want, whereas with an electrical solution, of course, you need to fire out of eclipse mode. So we have new guidance schemes, and in addition to that, we're looking into developing a robotic platform combined control design to capture cooperative and uncooperative tumbling targets in space, again, for deorbiting missions. And you see the picture with the green contour. It's a trial, the first trial we performed in this sense on the A400M, again, developing computer vision solution to be able to reliably address space rendezvous and proximity operations. More in detail, this is the movie of the last flight of the automated transfer vehicle. And what you see here is the approach of the ATV to the ISS with the actual images as taken by the cameras, the recognize and position model projected back in the image with the green contour, the superposition of the green contour and the actual image illustrate the accuracy of this very model based on detection and tracking principles. And so these are techniques we are further developing for rendezvous missions in space. Another very interesting application of this concept is the one we have just recently tested on air-to-air refueling operations. So this is a test flight performed on our MRTT, multi-role tactical tanker. This is an A310. It's our own flight test aircraft. The MRTT in its customer version is an A330 platform. We have performed automated contacts between F-16 of the Portuguese Air Force and our boom for automated refueling. This is normally a fully manual operation and a very, very complex one. You need a specific operator, a pilot called the boomer with 2 joysticks. With 1 joystick, he flies the boom. With the other, he commands the extraction of the refueling probe. And this system, based on algorithms developed for rendezvous missions in space, will enable automated contact and refueling in close tracking Bloom Auto mode. And I have tried this myself on the simulator. I can guarantee you it's, I think the Portuguese Air Force would be out of F-16 if it were up to me. So automatic control in space, challenges ahead. Looking at the constellation concept I have briefly touched upon earlier on, specifically OneWeb. We have hundreds of satellites, so a very, very dense constellation moving slowly from the launcher to the final orbit. So performing classical ground-based control for each satellite like we normally done in the last 10 years is totally out of the question. It would be prohibitive in terms of cost, in terms of human resources needed to do so. So we have several challenges in terms of orbit control and autonomy in this sense. We need autonomous onboard computation of trajectories and control commands with the handling of collision avoidance, both between satellites and between satellites and debris. These are handled on the ground today and will require more and more automation. So we are developing autonomous guidance solutions for safe orbit raising of such a complex constellation of hundreds of satellites. Also, the prediction of potential collision will remain on the ground. However, it's possible to upload, it will be possible to upload by telecommand the orbits of dangerous objects to the spacecraft, having then the spacecraft computing autonomously the required orbit avoidance. If you want to have more details into what we do in the space realm, when it comes to automatic and control, there will be further lectures from colleagues of Defense and Space throughout the day. I invite you to participate. And would like to conclude with an overall message. So you've seen the portfolio of our division is particularly rich and diversified, also within the space system segment. The space system segment is characterized by a very broad array of very different missions. The minimum common denominator, the pulsating heart, is one, and it's called control engineering. So automatic and control is not only a science, is not only rich of history and experience and expertise, but it's also the conditio sine qua non for the fulfillment of our future challenges and visions. Thank you very much for your attention.